Let's look at circuits. So a circuit is a loop through which a current can flow. And we'll look at a simple example. Let's use a battery, a couple wires, and a light bulb, and let's arrange them like this. If we do that, the light bulb lights up. Well, why does that happen? Well, that takes some explaining. Remember one thing before we start. A battery creates or supplies an EMF, a potential difference, across its terminals. And if a charge moves across that potential difference, that is associated with work, aka a transfer of energy. So a charge moving across a potential difference that's created by a battery is associated with some kind of work. Also remember, there are many types of energy. We've seen kinetic energy, gravitational potential energy, spring potential energy. Here we're going to talk about a new type called electrical potential energy. It follows the same rules as all other types of energy. It's just a different form of energy. So if we imagine a positive charge moving through this circuit, when that positive charge goes from the negative side of the battery to the positive side of the battery, it will gain electrical potential energy. The battery, through methods that we're not going to worry about right now, the battery transfers or adds electrical potential energy to the positive charge. So the charge gains potential energy as it moves from the negative side to the positive side of the battery, as it moves through that EMF, through that potential difference. Then, the positive charge moves through the wire. Nothing happens to the energy of the charge as it travels through the wire. The wire is made of a conductor, and essentially the charge just moves through it, just swims through it without changing its energy. Then it gets to the bulb. The charge gets to the bulb, and the bulb, through means that we're not going to worry about right now, the bulb takes some energy from those moving charges. In other words, the charges with electrical potential energy transfer their energy to the light bulb, and the light bulb converts it into light energy, which causes it to shine. This means that work is done in the bulb. Work is done in the bulb. Energy is transferred from the charges to the bulb. So there's also a potential difference across the light bulb. When the charges leave the light bulb, they have lost their electrical potential energy and they sort of sulk back through the wire to the negative terminal of the battery, where they start the whole journey again. So, the battery supplies a potential difference, which transfers energy to the charges. And as the charges move through the light bulb, the charges transfer energy to the bulb, which also has a potential difference across it. The current of the charges flows around and around. It gains potential energy from the battery, and then it loses potential energy to the bulb, around and around and around. So you probably have questions like, how does the battery keep supplying energy? Isn't it actually negative charges that are moving in the conductor, not positive charges? How does the light bulb turn electrical energy into light? These are really good questions. We'll learn more about batteries another time, but their energy is provided by chemical reactions. It's not a magic source of energy. It's just chemical potential energy being turned into electrical potential energy. And batteries do eventually run out of energy. That's why you have to change batteries in your TV remote. And yeah, for the charges, it is actually electrons that are moving, not positive charges. So in reality, the electrons flow in the reverse direction. And in reality, the electrons have more energy when they leave the negative terminal of the battery, and they have less energy when they arrive at the positive terminal. But it essentially works the same way that I've explained it with positive charges. And the light bulb, well, we'll explain how the light bulb works another time. Also, this type of circuit that I've explained is a specific type called a DC circuit, or a direct current circuit. It's a situation where the current travels in one direction continuously. This is the type of current that's created by batteries and electric cells, and it's the focus of this unit. But there is another type of current called AC, or alternating current. In those types of circuits, the current changes direction, goes back and forth. It goes clockwise, then counterclockwise, then clockwise again, then counterclockwise. And it usually does that many times every second. This is the type that's used for most applications. So it's the type of current that comes out of sockets in your home, type created by power plants. And it's a topic that we'll revisit another time. But let's look at resistance now. Resistance is a measure of how much an object resists current flowing through it. So an object will have high resistance if it opposes current flowing through it. And an object will have low resistance if it doesn't oppose current flowing through it. So like take for example conductors. Conductors allow free electrons to move very easily through them. So conductors have very low resistance. In fact, we almost always assume that conductors have a resistance equal to 0, that they do not oppose electron flow at all. Other objects like light bulb filaments or heating elements inside of your oven, those do have pretty high resistance, and they oppose the flow of electrons through them. But at any rate, resistance, the symbol we use for that is a capital R, sometimes a lowercase r in special situations, but R. And the resistance is defined as the potential difference across an object divided by the current flowing through the object. The unit of resistance is the ohm, which is written as a capital omega, and it is a scalar quantity. That ohm right there, you can see from the equation that the ohm is equal to a volt divided by an amp. An ohm is equal to a volt per amp. And we could even do some other tricks with the ohm. It's a volt per amp. Well, a volt is a joule per coulomb, and an amp is a coulomb per second. So an ohm is equal to a joule second per coulomb squared. Okay. Or we could also do it this way if we wanted to break it into fundamental units. This takes a little more work, but ohm is equal to a volt per amp. A volt is a joule per coulomb. A coulomb is an amp times a second. Okay, so we go through, expand the joule. An ohm is equal to a kilogram, meter squared, per second cubed, per amp squared, which is pretty terrible. And that is why we use the ohm instead of the fundamental unit. A resistor is something in a circuit which has resistance. Resistors are often the useful thing that's in the circuit, so the light bulb or the heater or what have you. Let's look at what happens inside of a resistor on a microscopic level. So in a resistor, when current flows through, I'm going to draw sort of a diagram of that, and here are the atoms that make up the resistor, and I'm going to draw the electrons as they flow through. As the electrons move through the resistor, as the current flows through the resistor, those electrons are going to hit those atoms. They're going to impact it. That's what's resisting the flow of electrons, is they're going to impact those little atoms in the resistor. And when that happens, when they collide, the electrons transfer some of their kinetic energy, some of their energy to the atoms in the resistor. And so the atoms gain energy. Now, one of the consequences of this is that if the electrons are transferring energy to the atoms in the resistor, usually that means that the atoms in the resistor are going to start moving faster. They'll gain kinetic energy. And let's see, if the atoms gain kinetic energy, that means the temperature of the object will increase, because temperature is just a measure of the average kinetic energy of the molecules in the resistor. So again, electrons flowing through a resistor will impact the atoms in the resistor, transfer energy to those atoms. The atoms will move around more, and the resistor gets hotter. It heats up the resistor as current flows through it.